Hello, cowboys and cowgirls. This is Dr. Johnson. I am one of the AP Stats teachers at Capella High School, and I welcome you to this lesson on sampling distributions of sample means. Last class, we talked about sampling distribution of sample proportions. Today, we're talking about quantitative data, and so it's sampling distribution of sample means. I want to start with this little demonstration right here. Suppose that our parent population looks something like this. We'll call this approximately normal. And I want to take a sample of size 5 out of this, and we'll take a sample of size 10 out of this. And I'll show you what's happening here. So we're taking a sample of 5, and that generates one mean right here. Then we take a sample of 10, and it generates a different mean right here. Maybe it's the same, maybe it's different. So this level right here is going to be our sample data. This right here will be a sampling distribution of sample means when the sample size is whatever number I specify here. And this is the sampling distribution of sample means when the sample size is this. So I'm going to do this again, but I'm going to do it many times. I'm going to change this to 16. So here we go. I'm going to select 10,000 samples from our population, our parent population. And in the second to the bottom graph right here, I have a sampling distribution of sample means. Notice here that the standard deviation of my sampling distribution is 2.26. Down here, I have, in the very bottom, I've got another sampling distribution, but this time my sample size was 16. And when the sample size is 16, my standard deviation of the sampling distribution is smaller. You can see the bottom graph is narrower than the second to the bottom graph. This one has a standard deviation of 1.25. So one lesson we learn here is that as the sample size increases, the spread of the sampling distribution gets smaller. Now I'm going to make it even more pronounced. We're going to change this from 5, and I'm going to see if I can make this, say, 25. We'll just do 10,000 again. And you can see again, as the sample size increases to 25, my sampling distribution of sample means gets very small. Now the standard deviation is 1. Now let's change it. Instead of having a parent population that's normal, let's change it and make it skewed. Like that. We have a right skewed parent population. I'm going to start out with means of, let's say we take samples of size 2 here and samples of size 25. Again, we'll take 25 here. Or, well, let's make it 25. And let's see what happens. I'm going to take 10,000 samples again. And now, well, we see one thing that we saw before. As the sample size went from 2 to 25, the spread of the sampling distribution decreased. Okay, here the spread, the standard deviation was 4.38. Here the spread of my sampling distribution is 1.24. But there's another thing I want you to notice. That is, the shape changed. When the sample size was 2, my sampling distribution of X bars, this is my sampling distribution of sample means, is shaped kind of like my parent population. It too is skewed to the right. But as my sample size increased to 25, my sampling distribution of sample means looks more approximately normal. So I want to go to my slides here, and we'll walk you through some of these. Hold on. There we go. So, for numerical variables, when random sampling with replacement from a population with mean mu, the sampling distribution of sample means has a mean of mu. So the mean of all my X bars is mu, as long as I was sampling randomly. That means that X bar is an unbiased estimator of mu. The center of my distribution of X bars is centered over mu. Here I have a proof if you want to go through that proof. Basically, the expectation of a sum is the sum of the expectation. So the mean of all my x bars, the expected value of my x bars, is equal to mu. Now, for numerical variables, when random sampling with replacement from a population with standard deviation sigma, so my population has a standard deviation sigma, the sampling distribution of sample means has a standard deviation given by this formula right here. This means that the sample mean x bar, this means that the standard deviation of sampling distributions of x bar is equal to the standard deviation of the population divided by the square root of n. So as n gets larger, you can see why the spread of my sampling distribution will get smaller. Okay? But I have to tell you this. This formula right here that I'm showing only works if the independence condition is holds or the 10% condition is met. So this formula works if we are sampling with replacement, but if we are sampling without replacement, we're going to have to show that our sample size is less than 1/10 of the population size. If the sample size is small compared to the population size, then the use of this formula is okay. This tells me that averages are less variable than individual observations. So the left and the standard deviation of x bar is smaller than the standard deviation of the population. To cut the sample standard deviation in half, by how much must you increase the sample size? Suppose I wanted to cut the standard deviation of my x bars in half. What would I have to do to n? I would have to quadruple n. Okay, there's a proof at the end if you'd like to go see that. Now, if the population distribution can be modeled with a normal distribution, the sampling distribution of sample means x bar can be modeled with a normal distribution regardless of sample size. Putting this together, suppose that x1 through xn form a random sample from a normally distributed population with mean mu and standard deviation sigma. Then the sampling distribution of x bar has a normal distribution with a mean of mu and a standard deviation given by the formula that we just discussed. So we can say that x bar is normally distributed with mean of mu and standard deviation of the population standard deviation divided by the square root of n. Now I want to talk a little bit more about the shape. Remember, I showed you that if the parent population shape is not normal, the sampling distribution appears to be normal or approximately normal if the sample size is large enough. So let's talk about that. If the population distribution is not normal, then the shape of the sampling distribution of x bar looks like the population distribution if the sample size is small. Remember, we saw that in my little simulation at the beginning. But the sampling distribution approximates a normal distribution if the sample size is large. And here we're going to say that the sample size is considered large if it is greater than or equal to 30. So let's look at these graphs on the right. And you notice that the left-hand column, the column where we start out with a normal parent population, then all of my sampling distributions are normal. Okay. But now I want to look at the three distributions on the right. I have the uniform distribution, an exponential distribution, and a parabolic distribution. And you can see that if the sampling distribution is small, say n equals 2, the sampling distribution kind of looks like the parent population. But as the sample size gets larger, down to n equals 30, then my sampling distribution is approximately normal. Here's another graph that shows about the same thing. I'm going to skip it for now. So on this slide, I just want to talk about the last bullet point. As the sample size increases, the distribution of means will approach the normal distribution regardless of the shape of the population distribution. This last principle right there is called the Central Limit Theorem. This is a very important theorem in all of stats. Basically, it makes inference testing possible. Here it is. Given any population with mean mu and a finite variance, the sampling distribution of sample means will become approximately normal when the sample size is sufficiently large. And for that, we're going to use as our rule, n is greater than or equal to 30. Okay, so here's a summary. If the population variable is normally distributed, then the sampling distribution of sample means is also normally distributed regardless of sample size. For other random variables, the sampling distribution of sample means is approximately normally distributed as long as the sample size is 30 or more. Again, in the case of the use of the central limit theorem, the second bullet point, the result is that we have a distribution that is approximately normal. You must have that word approximately in there. So here are the three conditions to doing our analysis. We have to make sure that the data comes from a well-designed random sample or a randomized experiment. If the sample is not random, then we cannot make inferences to the population. The second condition is that the observations are independent or the 10% condition is met. When sampling with replacement, we need to check that the sample size is less than 1/10 of the population size. That's what enables us to use the formula. I should add here that if you are doing an experiment, you do not have to check the 10% condition. If you are doing an experiment, you do not have to check the 10% condition. Lastly, the third condition is that the parent population has to be normal or that we have a large sample. So the population has a normal distribution or the sample size is large. If the population distribution has an unknown shape and a sample size is small, we're going to let you use a graph of sample data to assess normality, but we're going to talk more about that later. And here's just a summary of what we talked about. When these conditions are met and the population standard deviation is known, the sampling distribution of sample statistic x bar has a mean of mu, a standard deviation given by that formula, and and the shape of the sampling distribution is either normal or approximately normal. Again, do not round intermediate results because that gets amplified when we get to our final conclusion. Sample size needs to be a whole number and should always be rounded up. So for calculating sample size, we have to round up. Here are some testing suggestions. I'll get back to that later. Here's a proof that the variance of x bar is equal to the variance of the population divided by n, if you're interested in that. This slide talks about why we are using the 10% condition. You're welcome to look this over, but this is not required. More on that. And so I'm going to end the slides now, but I want to go through a practice problem. So let me find my practice problem. Here we go. We'll use this one right here. So at the Peanutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15. So when they're putting these peanuts into a jar, we don't always get the same quantity. The mean is 16.1 and the standard deviation is 0.15. Suppose that we randomly select 10 jars. What is the probability that the average contents weigh less than 16 ounces? So I'm imagining that they put on the side of their jar that it contains at least 16 ounces. We are going to use the ICCI method again, so we begin by identifying. Let X be the average weight of the contents of a random sample of 10 jars. We want to find the probability that a random sample of size 10 will give a sample mean less than 16 ounces when the true mean of the population is 16.1. That is, we want to find the probability of getting a sample mean of less than 16 when the true mean is 16.1. Now we have to check the conditions, but we want to start out with a sentence like this. If the conditions are met, we will use the sampling distribution of X bar. That's the name of this procedure. I want you to mention the name of this procedure. It's the sampling distribution of X bar to calculate the probability. Now I check my three conditions. The randomness condition, yes, it says we are selecting randomly, so we've met that. The independent observation, or the 10% condition, well, this isn't independent because we are selecting without replacement. So we have to check the 10% condition. We don't know what the population size is, so we're just going to say this. It is reasonable to assume that there are more than 10 times 10 or 100 jars of peanut butter. So our sample size is less than or equal to the population size divided by 10. Now, in this case, we are told that the distribution of weights, the population distribution, is approximately normal. So because of that, the sampling distribution is also distributed normally. But we could give you a different problem and say that the parent population is skewed, but our sample size is, say, 40 or 50. In that case, the sample size is large enough to use the central limit theorem to meet this condition. So now we've met all three conditions. We just want to find out what the center, spread, and shape of our sampling distribution of X bars is. Because the sampling was random, the mean is equal to 16.1. Because the 10% condition is met, we can use the formula for standard deviation of X bars. So I plug in my numbers. I take my population standard deviation of 0.15 and I divide it by, the square root of 10. And that gives me a standard deviation of 0.0474. And because the parent population was normal, the sampling distribution is also normal. So we know now that X bar, all my X bars are normally distributed with a mean of 16.1 and a standard deviation of 0.0474. Now we want to find the probability of getting an X bar less than or equal to 16. So this is a chapter 2 problem. The z-score for 16 is, well, I take 16 minus 16.1, the mean, divided by the standard deviation, which we just calculated to be 0.474, and I get a z-score for 16 of minus 2.11. So now I draw my graph. Remember, you always have to draw a graph here. Draw my normal distribution. I put my, let me see here. This thing should be a little bit further out here. I'm going to put 16.1 is my mean. That goes over here. So 16.1 is the that belongs right there in the center of the graph, and this bar is located at 16, or 2.1 standard deviations below the mean. So this is my borderline. It's located at 16, and I want to find the area of this left little tail here, that left little tail. So I turn on my calculator. I go to normal CDF. The lower boundary is minus 1,000. The upper boundary is 16. My standard deviation is equal to, well, we calculated up here to be 0.0474, but I could plug these numbers right into my calculator. And the mean is 16.1. That tells me that when I hit execute, it tells me that the probability of getting an X bar less than 16 is equal to the probability of getting a random Z less than minus 2.11. And my calculator tells me that that probability is 0.0174, a small number, less than 2% of the time. So I interpret, this is my conclusion, the probability that a random sample of size 10 will give a sample mean less than 16 is this very, very small number. So that is it for today. Thank you very much. I'm ending this presentation, so thank you very much.